Hello, welcome to our calculus video lesson on rules for differentiation. Please note that one of the benefits of a video lesson is that you can take it in small bits, you can pause, you can rewind, you can even fast forward if I am getting to be too boring for you and you think that you can jump ahead and do some problems and then you can see if you get them right. And if you get them right, then we are all square. So just bear that in mind. It has some advantages. A disadvantage is not asking me questions immediately. So please do mark in your notes if you have questions that don't get answered in the video. That is something that we could take care of tomorrow in class. Also tomorrow in class, make sure that you do bring your textbook with you. You will definitely want your own book. We will be working a problem set the entire class period, and you can work at your own pace for that. Okay, you can read here the goals I have for this lesson. There are a lot of different rules for differentiation. This is the infamous shortcut rule lesson. So that is exciting for those of you who are sick of limit definition of derivatives. And we will look at the sine and cosine function derivatives, and we will look at average velocity versus instantaneous velocity. Okay, some notation reminders. Derivatives can be written in a lot of different ways. The quickest way is probably to use a prime sign, which also can be applied within function notation as f prime of x. Sometimes there are situations where it's nice to just write something like this. This means the derivative with respect to x, meaning I am identifying my independent variable with that little slot there that I underlined. And then in the parentheses, you put whatever it is you are taking the derivative of. And then the last version, or a little twist on that, would be to just say, well, I am taking the derivative of y with respect to x, okay? And this last one is called Leibniz notation, credited to the mathematician Leibniz, who we believe first came up with that. And it really is reminiscent of where a derivative comes from, which is slope. And slope is the change in y versus the change in x. So the d stands for derivative, but you can also think of it as being as something that came from delta y, delta x, okay? So all of these things mean derivative, and I just wanted to point that out. You do need to be flexible in your notation and understand all of them, not just adopt one of them and ignore the rest, okay? Shortcut rules for differentiation. First one is called the constant rule. So the way that that is written right there, it means the derivative of a constant. Now, a constant is a numerical value with no variable in it at all, such as 3, the derivative of 3, the derivative of 7, the derivative of -2, the derivative of pi. All of these things would equal 0. And that should make good sense, because if you think about this in terms of being a function, and so say this is some value c, the function f of x equals c is a horizontal line. And what is the slope of a horizontal line? Yes, it is 0. Okay, so this is the point here, 0 comma c, right? And then the slope of that is 0, which is why the derivative is 0. Okay? Next one, power rule. Power rule, we've kind of hinted around it. Some of you know it. Some of you have recently asked me, is this what's happening every time? Okay. Understand that in this expression, x is a variable. And n is understood to be a numerical value, okay? N is a number. Okay, and so we are going to just write this down, I guess, okay? The derivative rule, the shortcut that you would get from doing limit definition of derivatives to prove this, is that the exponent becomes a coefficient, this number here, and then the exponent shrinks by 1. Okay, it goes down by 1. And so that is our power rule, okay? It would even apply to this situation. X to the first. Bring the 1 down in front. You get x to the 0. What is x to the 0 as long as x itself isn't 0? It's 1. So you have 1 times 1, which is 1. And that should make good physical sense or mathematical sense, because the function y equals x is this line here. And what is the slope of that line? Slope is 1. So the derivative, or the slope, of x is 1. That's all that is saying. All right, down here we have the constant multiple rule. I don't know, I never really use this name, but what it's saying to us here is that this is some number. That's the setup. So C is a number or a constant, and x to the n is like in the previous question or previous statement. X is a variable, n is a number. And so this constant is just going to ride along, okay? And then the derivative of this. Okay? So that is the constant multiple rule. It comes from the fact that when you have a limit, like think about the limit definition of a derivative. You have c, some constant times blah, blah, blah. Okay? This c, there's a property of limits that says that c can come on out, and you still have the limit of blah, blah, blah. Okay? So it's the same thing because derivatives are defined from that limit definition of the derivative. A constant can kind of, as you might think of it, come out. Okay? Yeah. I think in general we could say it this way. Okay? In general, might be better to write this actually. In general, if we are taking the derivative of a constant times a function, then that's going to be the constant times the derivative of the function. I like that line. You should have that line in your notes. That's a good one. Okay? Because I'd stated it up here just relative to taking, to dealing with powers, but it really is true for all functions. If anytime you have a constant times a function and you're finding its derivative, the constant can kind of just ride along. Okay? All right, sum and difference. Sum and difference are exactly as you might expect them to be. If you're taking the limit, remember thinking about limits. If you're taking the limit of two things added or subtracted, you can take the limit of each part. Well, because derivatives come from limits, that means that we can just take the derivative of f. Oh, that looked really weird. Actually, I'm going to write it differently anyway. Okay? We can take the derivative of f of x. Let me write it with a prime sign. And then we can either add or subtract depending and have the derivative of g of x. Okay, sorry you guys, I just realized that I recorded that. I thought I had it on pause. The writing was not aligning very well with the smartboard, and I'm sorry I recorded that. This is non-editable software I'm using, so if I make a mistake, I have to either start over or just go with it. So I'm going with it because I'm not doing these 8 minutes over again. Okay, there is a section here of problems. I'd like you to try these. First pause the video and then try the problems and then see if you got them right. Okay, so here are my answers. I'm going to just point out a few things. The first one, very straightforward. The second one, notice I rewrote the derivative statement first so that applying the power rule was more simple for me. I highly recommend that strategy. I used that same strategy over here. I took this radical and rewrote it as a power, so applying the power rule would be more straightforward. This problem in green is pretty clear, I hope. You just do the derivative of each of those pieces. The derivative of the -3 is 0. And then here I did do, again, using a little strategy, I messed around with what I was given first before I took a derivative. So first I took care of that exponent in the denominator. Then I pulled out that constant, so I was left with as little as possible to differentiate. And then I took the derivative from here to here using the power rule. Please pause and look at this if you need to. Otherwise, we're going to move on. All right, trig derivatives. Now, we have already hinted a little bit at what some of the derivatives, the sine and cosine might be. Some of you saw this when we were sketching derivative functions. Some of you saw it. We saw one of them in the local linearity week. I'm actually going to formally prove them now, a little bit of rigor for our class. So using the limit definition of the derivative, I wanted to take the derivative of sine. That would give me sine of x plus h minus sine of x all over h. Just applying f of x plus h minus f of x all over h, okay? Then we get to, I know it's very exciting, but we get to use one of those lovely identities back from the days in our trig class, okay? So right here is a statement to which I could apply the sum formula, S-U-M, sum formula for sine. I know, it's very exciting. It's probably been a few months since you got to do that, okay? So here, I know that sine of something plus something goes sine, cosine, cosine, sine. So it would be sine of x cosine of h plus cosine of x and sine of h. That is just an identity from back in the day, okay? So the part that matches up there would be this. This part that I highlighted in blue matches the part up above, okay? That's a trig identity. Very exciting, okay? Now, in the next step, you get to see a very, very cool limit statement pop up, okay? We're going to do a little factoring, okay? So what we're going to do is we're going to factor out, let me think. I think it works best if I factor out negative sign. Pretty sure that's right. Okay, and then we factor out negative sign from there, and then we'd have, hold on. Okay, so I want to take negative sign out, but the terms I'm going to take it from are actually this term and this term here, okay? So the negative sign is with a 1 from this last term, and then it is with negative cosine from that first term that I underlined in red. And then I also have this other guy, so plus cosine x sine h. And I'm also going to split this into two fractions. This has an h and this has an h. Okay, so take a look at that. This part is right here, okay? And then the parts with the wiggly underlines are in the first fraction. And I also factored out a negative sign. Maybe that was too much for one step. So again, the advantage is you can pause it and take a look at it if you need to. All right, now this is cool. This is really good. Okay, look at this. Do you recognize that piece? Especially thinking about this being a limit. That's a limit that you guys know, right? That's one of the ones I had you kind of memorize. Remember that? This limit is 0. So it doesn't matter about this part, the negative sign. Who cares? That whole limit is 0. Now I have the limit of this part over here. So let's think about that, okay? I recognize something in here. What's that? The limit of sine of x over x, so to speak, or sine of h over h in this case, since we're talking h's. That limit is one I had you memorize as well. That's 1. So I have plus cosine x times 1. Well, if you simplify that, easy peasy, that's cosine. So, therefore, the derivative of sine of x, which is what this whole chain of stuff started with, is cosine of x. We've seen this before, but now we have proven it. Okay. On the next slide, we are going to derive the derivative of cosine. Same idea, using the limit definition of a derivative. We start out f of x plus h minus f of x all over h. Fantastic, okay? Now we're going to use one of those lovely trig identities, right, on the part that's right here. Okay, so that part is something I can do with the trig identity. It's the one that goes cosine, cosine, sine, sine. So it's cosine x cosine h minus sine x sine h. And then the negative cosine or the subtracting of cosine just follows, and I've got an h down here. Okay? In the next step, we're going to do creative regrouping and factoring. Okay, so what I'm going to pay attention to is the fact that cosine of x shows up in 2 of the terms. Okay, so I'm actually going to write this a little bit out of order. Here is negative cosine of x. And if I factored that out from this part, I'd have a 1. If I factored it out of this part, I'd have minus, excuse me, minus cosine h. Okay, that's a 1. I'm just making it worse. Okay. And this would be all over h. And then over here, the only term I'd have left would be this piece over here. It's very analogous to what we did on the previous slide, okay? So this, the signs over an h, and together, okay? Taking the limit, okay? And because I can take the limit of each part of this, I actually probably should have written a limit in front of each little piece here. But this limit with this, that part is equal to 1. So I've got negative sine x times 1. And this limit with that is equal to 0. So we have just the opposite of sine. So if you remember where we began, this whole statement started with figuring out the derivative of cosine. So therefore, the derivative of cosine is the opposite of the sine function. These are two things I expect that you will know from now on. You don't need to actually derive them, but I have proven them for you so you can trust that they are truths, okay? The next piece has a few questions for you to try. Pause the video and try these two. Okay, here is my work for these two questions. Verify that you got both of them correct. Negative 5 sine x for the first one, 6 plus cosine of x for the second one. All right, the last little section that we have to work on has to do with position, velocity, that kind of stuff. So those of you taking physics or who have taken physics, that's a boost to doing well in this type of problem in calculus. It isn't necessary to have a physics background, however, to do well with these. Okay, so understand that if we're looking for an average rate of change, that is calculus talk for just find the slope. Okay, average rate of change. So if I had a graph that involved time versus position. So position would be the distance I have traveled or how far I am from a fixed point in space. I might have some sort of a position function that looks like this, let's say. Okay, nice parabolic position function. And if I were looking at two different points in time, let's say this is point A and this is point B in time. I look at my position at each of those moments, and what I'd be finding with the equation above is the slope of that secant line. That's my average rate of change. Now, when the original function is a position function, the slope of that secant line represents what we call average velocity, okay? Average velocity is over an interval, okay? And it's the change in distance versus the change in time. That's all it is, okay? Velocity you can think of sort of like speed, except that velocity has a direction associated with it. So if you just define it in some way, like you say, if I'm moving forward, that's positive. If I'm moving backward, that's negative. If I'm moving to the north, maybe that's positive. And if I'm moving to the south, that's negative, or something like that. So you have some sort of a sign associated, S-I-G-N, that kind of sign associated with your speed, and that makes it a velocity statement rather than a speed statement. Okay? Here's a problem that has an average velocity question. Okay? It says the height in feet of a free-falling object at time t in seconds is given by that function. Okay? So I know this is a position function because it's describing height. It's describing where something is. And here is that position function. If I'm looking for average velocity, I'm just looking for the slope of a secant line. So I need 2 points. Okay, it's set on the interval from 1 to 2. So I'm going to find out the position or the height of this function at 1 and at 2. At 1, I'd have, let's see, negative 16, 1 squared plus 180, which is 164. And at 2, I'd have negative 16 times 2 squared is 4, plus 180. When I work that out, let's see, that would be 116. Okay, now to do average velocity, it's really just finding the slope of the secant line, and I've found slope for ages, and so have you. So this should not be scary. Okay, just use your slope formula, and you find out, hey, oops, except that I think I flipped those, didn't I? I was talking about how awesome slope is. Okay, 2 was with the 116, so if I do 2 minus 1 here, the 2 has to be with the 116. Sorry about that. Okay? Just order-wise, you have to put the ordered pairs on top of each other. In other words, or in other visual, these 2 come from the same point. These 2 come from the same ordered pair. Okay? I didn't have that at first. Sorry about that. And so when I work this out, I would get 1 on the bottom and negative 48 on the top. So negative 48 divided by 1 is negative 48. And then the units, I have to look back here. It says that the height was in feet and the time was in seconds. So I had feet over seconds here. So this is in feet per seconds. Feet per second. Okay? So my final answer would be this. That's the slope of that secant line, or the average velocity over that interval. Now, the great thing about calculus is that it allows you to calculate not just average, but it allows you to calculate instantaneous. An instantaneous velocity is an example of an instantaneous rate of change. Instantaneous rate of change, that's just the slope of the tangent line instead of the slope of the secant line. So this isn't anything new or scary to us, I hope, okay? So I have some writing here explaining how as the 2 points shrink together, you're really just getting the derivative. Yay, derivative. Okay, so that's what I'll write. I'll write this out, okay? So an instantaneous rate of change is the derivative or the slope of the tangent line at some particular point. Okay, so for those of you who need the above mathy stuff in words, okay? So an instantaneous rate of change is just the derivative or the slope of the tangent line at a particular value, okay? The derivative's value at a particular value, all right? Then, oops. Here's an example. Give the position function of a diver who jumps from a board 12 feet high with an initial velocity of 16 feet per second. Then find the diver's velocity function. Okay, well, in algebra, like your second year algebra class, AAA or AATH or whatever, you learn this, okay? And I give it to you again. This is something that you probably should commit to memory. Okay, so it is a fact that 1/2 g is the gravitational force times time squared plus initial velocity times time. That's what v sub 0 is, initial velocity, plus s sub 0, initial position, gives you the position of a free-falling object, okay, relative to time. So we are going to plug in the things that we know, okay? We know that the gravitational constant is negative 32 when we're dealing in feet. Okay, so negative 16 is what would end up here. Negative 32 times 1/2, t squared. Said in the problem, the initial velocity was 16 feet per second, so 16 goes in that slot. And they said that the board that they jumped off of was 12 feet high, so that's a 12. Okay, so here is the position function. They wanted us to give a velocity function. Well, that's actually quite easy to do in calculus because we know the derivative of position is velocity. That's a good thing to know. That should have like a big box around it. Okay, the derivative of position is velocity. So I take the derivative here, I'd get negative 32t plus 16 plus nothing else, plus a 0, because 12 is a constant. So that's our that's our velocity function, yes, okay? The next question actually doesn't use that velocity function. It uses the position function. They want to know when the diver hit the water. Hitting the water, that's a position. It's the position where your height above the water is 0. So I want to know when, look at that blue line up above, okay, this guy. I want to know when the position is 0. So this is just solving a quadratic equation, okay? This is factorable. I could factor out a -4, and then I could factor the rest of it. Let's see here, what would this be? Okay, so -4, and then this factors to 2t minus 3, 2t plus 1. And if that's set equal to 0, that means that t would have to equal 1.5 or -0.5. Now, one of those doesn't really make sense in the context of the story, and that's -1/2, because time would start from positive values. All right, start from 0, really, okay? So a positive answer is what I want. So after 1.5 seconds, the diver's going to hit the water. Now they want to know, what is the diver's velocity when they hit the water? Well, they hit the water at 1.5 seconds. So what is the diver's velocity at t equals 1.5? Is really what the question is asking. And up above, we found the velocity equation. It was right there. So velocity, I'm just going to copy it down, was equal to -32t plus 16. So velocity at 1.5 is -32 times 1.5 plus 16, which I think turns out to be, if I did my arithmetic right, -32 feet per second is the diver's velocity when he or she hits the ground. All right, that's all I have for you. That's kind of on the long side, by the way, for a video lesson. I do try to make them a little shorter than this, but there was a lot to go over. So hopefully tomorrow, when you bring your notes to class, your book to class, and your homework notebook to class, I will be able to give you the entire class period, and you'll get all of your assignment done in class and can ask lots of questions. See you then.